All right, in problem 27, we're told that quadrilateral ROTS has vertices labeled. And we want to show that if the midpoints of the sides of the quadrilateral are connected, then the figure formed has opposite sides that are congruent. So there's a lot of things going on here. We've got midpoints and we've got opposite sides congruent. So basically, first of all, we need to find out the locations of P, Q, M, and N. Those are the points that we're going to be looking at. And for each of them, we're going to use that midpoint formula again. The midpoint is x1 plus x2 over 2, comma y1 plus y2 over 2. I'm going to write these individually. So first we're going to find out P. P has 0 plus 2, so that's 2 over 2, or 1. 4 plus 0, that's 4 over 2, which is 2. So P has coordinate 1, comma 2. Q, let's look at Q. It has 6 plus 2, which is 8, over 2 is 4. And 6 plus 4, which is 10, over 2 is 5. So that's coordinates of Q. M has 8 plus 6, which is 14, over 2 is 7, and 0 plus 6 is 6 over 2, which is 3. And then last but not least, N has 0.0 plus 8, which is 8, divided by 2 is 4, and 0 plus 0 is 0, divided by 2 is 0. So basically, we now want to know if we connect all of these points, will the opposite sides be congruent? And we can do this in several ways. There's definitely a longer way and a shorter way. I'm definitely going to talk about the, I'll tell you about the shorter way, but also I want to make sure that you understand the distance formula. I think that the distance formula is probably how they want you to use this, how you want to use this. And basically, we can find the distance between any 2 points by taking the square root of x2 minus x1 squared plus y2 minus y1 squared. And we can apply this to all 4 of these points. We can find the distance from P to N, we can find the distance from Q to M and compare. Then we can find the distance from P to Q and from M to N and compare those. Basically, let's get you started off here. The distance from P to N is going to be the square root of P to N. So 4 minus 1 is 3 squared, plus, I'm going to go with the y's now, 0 minus 2 is negative 2 squared. 3 squared is 9, plus 2 squared is 4, so 9 plus 4, so this is going to be square root of 13. I can find the distance from Q to M. So from Q to M, we've got 7 minus 4 is 3 squared, and 3 minus 5 is negative 2 squared. So you can see 3 squared plus 2 squared, we know already this is going to be root 13. So Pn and Qm are congruent. Now the distance from P to Q, we've got 1 minus 4 is negative 3 squared, and 2 minus 5 is another negative 3 squared. 3 squared plus 3 squared, that's 9 plus 9, or the square root of 18. And I could simplify it, but I don't actually need to compare it to another length. The distance from N to M is 4 minus 7, which is negative 3 squared, plus 0 minus 3, or yet again negative 3 squared. Negative 3 squared plus negative 3 squared, we already saw, was root 18. So yes, they are in fact congruent. Just one more quick way that you could do this if you wanted to. We know that opposite sides are congruent in a parallelogram. So an altogether different method of approaching this is basically to show that it's a parallelogram. We can show it's a parallelogram if the diagonals bisect each other, meaning if they have the same midpoint. So if I found out the midpoint of PM and compared it to the midpoint of QN. And if those were in fact the same point, then the diagonals would bisect each other and it would have to be a parallelogram. And if it was a parallelogram, the opposite sides have to be congruent. Let's just check that really quickly. The midpoint of PM would be 1 plus 7, which is 8, divided by 2, and 2 plus 3, which is 5, divided by 2. Let's just check QN really quickly. We'd have 4 plus 4, which is 8, divided by 2, and 5 plus 0, which is 5, divided by 2. Both of these methods completely work, but this tells us that PQMN is a parallelogram, so therefore opposite sides are congruent.